Welcome to all of you. Today we will discuss one of the famous feature extraction technique, that is a principal component analysis, and its implementation by using a Python programming.
So let us discuss about principal component analysis. So by using scikit-learn, we will try to learn how to implement principal component analysis. So basically, PCA is a feature extraction technique. So let us quickly revise the essence of this PCA. So it is basically used to remove the curse of dimensionality, right? So over the data frame, if it is having a number of features, so after applying the PCA, basically we extract the features, right? So that's why we call it as a feature extraction. So it is not a feature selection, it is a feature extraction technique. So basically by using PCA, we generally convert the higher dimension data into lower dimension. So that is the essence of that. Let me, give you the anal. It is the same, quietly same like this picture. So if you see this picture thoroughly, so basically photographer took pics of 3D object, which is which are there in the stadium, so that he can use this pics in this in his publication house, right? So basically what he does, photographer try to capture 3D information into 2D pics by moving around at a different angle, right? Same thing PCA does. It reduces the information from higher dimension to lower dimension without losing the essence of the information. That is very important part. So basically if you ask what is the benefit, if you will apply the PCA, then what is the benefit of that? So basically by doing this transformation from higher to lower dimension, we are going to be minimize the size of the data. If size is getting down, means we are doing a faster execution, means machine learning will perform optimally, right? Because computations are getting reduced. Basically PCA also help us to reduce the data redundancy, right? So these are the important part of that. Now it also help us for doing the visualization. So as you know, as a human being, we can also, we can see up to the 3D, right? So what if I am having a, let's say 10 column data? So we cannot visualize 10 column data, right? So what we do is basically by applying this PCA on 10 dimension data, we generally convert the higher dimension to lower dimension like 2D or 3D, and after that we can plot it and visualize the data, right? So let us now dive into the code to understand how this PCA can be implemented. So for PCA, what it is, I took this iris flower data set to reduce the dimensionality. So this data set contained basically 150 rows having a 4 column in each row. So to load this data set, we can call this load iris function from the dataset module. Now this code will display the information about the dataset. This iris is a bunch object. Hence, to see this object, we have to refer this iris dot data, right? So from this code, we can see that there are this 4 column, but we do not know the column name, right? You may see here 4 columns are there, but we are unable to know about the column name. To know the column name, we have to display the features name, right? So for that regard, I did this, right? So by executing this command, it will, you'll be aware about the features. So the 4 column names are like sepal length, sepal width, petal width in centimeter, right? So this column values decide which type of flower it is. That means iris flowers are classified into 3 types, as we are knowing that it is a setosa, versicolor and virginica, depending on this column value, right? So let us add this column name to the data row and make this data frame X, right? So we have created one data frame. Now you must see, you may visualize it. Now see here, X is our data frame that contain the independent features, or you may say it as a input, right? Similarly, we can have a Y that represent the dependent variable are the target values, right? So here Y is 1D array that contain this target values. So now see here, this value 0 indicate the flower is setosa, 1 indicate as versicolor, 2 indicate the virginica, right? Now these are the steps basically we follow for for applying the PCA. So these are the algorithmic steps which we have to follow. So this iris data flowers data set contain this 4 column. That means the dimensionality of data is 4. Let us practically apply this PCA and make it down to one dimensional data, right? That is our intention to behind learning this PCA. The first step is we have to normalize the data or fit the data in between a minimum and maximum value. So for this purpose, we can use either min max scalar, or you can go with this standard scalar, right? Basically, the idea behind this standard scalar is that it will transform our data such that its distribution will have this mean value 0 and standard deviation of 1, right? So that is the idea behind it. Now, this standard scalar is a class of this pre-processing module of sklearn package. Hence, we can create object of this this class, standard scalar class. Now, to convert the data, we have to call this fit transform method on this X data frame. So now my data has converted. Now, after that, the next step of PCA is we have to create the covariance matrix. So now this S scaled represent the converted, or you may say the normalized data. Now this can be used to create the covariance matrix. So basically, if you are already having idea about this covariance matrix. So basically it represents the variation and covariation of the variables. The columns of the data will become a row in the covariance matrix. Hence, what we does while we create this covariance matrix, we should first transform, right? We first convert the column of the data into the row, right? So that is the idea behind it. So after that, the next step after creating this covariance matrix, the next step of PCA is we have to create the eigenvector, eigenvalue and eigenvector. So this eigenvector is a straight line onto which all the data points should be projected. Ideally, this eigenvector should have a maximum magnitude so that it can accommodate all the data point without any loss, right? That is the intuition behind that. So to create this eigenvector, we have to use this EIG function, which is available in linear algebra module of NumPy, right? This is a linear algebra module of NumPy package, right? When this EIG is called, when this function is called, it returns basically eigenvalue and eigenvector, right? So this is a eigenvalue and eigenvector is returning. So we can calculate basically after this value, we can calculate the fraction of each eigenvalue compared to the sum of all values. So basically this gives us an idea of percentage of each value, right? So you may see here maximum eigenvalue is found in 0th row, right? This indicate that 0th column in eigenvector. So this 0th column can be obtained by transposing the row and taking the 0th row like this, right? So we are projecting this S scale data on the eigenvector, and that can be done by using this dot method, right? So that we have done over here. Now if you observe this projected X data, it contains only one column of data, that is one dimension data, right? So if you see the output of this is the 1D data. In this manner, what has happened actually? The actual X data was in 4D. Now after performing this many steps of PCA, this original 4D data has been converted into 1D, right? So that is the idea. After this transformation, now I can use this 1D data and I can apply any machine learning model, right, to train the model and to perform the predictions, right? Now, if we draw a line plot that shows the relationship between data point without showing the regression line, we will have a more clarity about how this data is distributed. So for that, I have plotted it. So basically, we are using this three color, right? So three color data points that represent three target value, like a Setosa is 0, versicolor is 1, and Virginica is 2. But important part over here is all of them are shown on a straight line, since they all are projected into one dimension, right? So that by seeing the outcome you may understand this part. Now we can also do we can also apply this PCA by using the sklearn by using this method. So PCA class itself will create the covariance matrix, eigenvector, and finally project the data on that eigenvector that we can do by using this PCA class. So what we are doing over here, first create an object of PCA class. So I am creating one of the object by using this PCA class, and here we have to pass the this n component value, right? So this specify the parameters, right? So after that, now we apply this PCA on S scale data and obtain the final data using this fit transform method, right? We got the projected X data. Using this data, we can create the data frame called DF1, right? So already we did it previously, right? So now let us draw the line plot to see that data is one dimension and distributed along only one axis. So you may see over here, the same result which we have obtained over here, the same result we are getting by using the second method as well. So they both are same actually. They indicate that data is reduced from 4 dimension to 1 dimension. The same can be verified by displaying the shape of data before and after this PCA, right? So you may see the dimension is 150 by 4. This was earlier, that was with the original data, and this is after this transformation, right? So this is the outcome of that. Now once we have done this transformation, now the next step is we can apply any machine learning model, right? We can use any machine learning model to by using this data we can train our model. So what we are doing is we are already knowing this train test split method. Now I am having this projected S-shaped data, so that is a reduced dimensional data. So if you recall, this train test split, this data dimension should be in 2D, right? But here I am getting in one dimension. So what we have to do is we have to convert this one column into 2D, and for that regard we are using this reshape method, right? So after doing this, now my data has been converted into 2D. Fine. So again, if you apply this method, it is going to be given this 4 value as the outcome. Now what we want to do is, let's say I want to apply this support vector machine on the I want to use, right? So basically this SVM is present into this sklearn package, and this is a module of that. So here we have to make an object of that, and now I am training my data. I'm training my model with respect with this data. So once we have done it, now my model has been trained. So if you want to check the accuracy of my model, so the accuracy of model is nothing but 0.8. That is nothing but 80%, right? So 80%, that is the accuracy of my model. So still 20% of chance that my model will do the bad predictions, right? That is the meaning of that. Now, after this, we can give the value of this sepal length, sepal width, petal length, and petal width of new flower, and we can ask to predict the type of flower from our model, right, which we have created. So what we have to do is we have to convert this value by using this transform method of standard scalar, right? After doing this, what we are doing, we are apply PC on this scaled value and reduce them into one dimension, right? So to predict which flower it is, we have to now apply this predict method. So ultimately it is giving you the outcome as 1, which is standing for what? The versicolor, right? Now this is the when you want to transform the 4D data over the 1D. What if I will ask you that transform this 4D data over 2D? Now see, the steps of PCA is the same, right? The same data set I have taken over here as well. So all this step we have followed in our previous method, which we have seen, right? So this given steps are same. Now what we have to do is over here, once we find out the eigenvalue and eigenvector, then after that we have seen the which are the influential eigenvalues that we have find out. Now after that, here we have to find out the two principal component with respect to this vector. We have to find out the vectors, right? Two influential vectors corresponding to the two influential eigenvalues, right? Once we have done it, now we have to plot, right? So if you plot this PCA, PCA1 and PCA2, so you will see that we are basically converting the 4D into two-dimensional data, right? So once we have converted, the next step is we can apply any machine learning model on that data. So if I will plot it, so you will see this, the 4-dimensional data has been converted into this 2-dimensional data. So these are the color which is standing for this setosa, versicolor and virginica. So that is the idea behind the PCA, how PCA basically works, right?
Now let me summarize whatever we have learned so far in this principal component analysis. So this PCA is a method to reduce multidimensional data to lower dimension while retaining most of the data. Basically this PCA, we use the principal component that is also called as eigenvector. So this eigenvector is a line with a maximum magnitude and a proper direction such that maximum number of data points can be projected on it, right? So this PCA reduce the number of columns, hence it is useful to speed up the machine learning models. Here basically for calculating the principal component, we use the covariance matrix. So this covariance matrix is a matrix that shows relationship between various features or columns. See, if if both variable tend to increase or decrease together, then the covariance is called as positive. Now if one variable tend to increase as other decrease, then covariance is called as negative, right? Since this PCA works on only normalized data, we have to convert the data in between maximum and minimum value. So this can be done by using mean max scalar or standard scalar. Now to achieve more accuracy for any model, it is better to use high volume of cleaned data for training purpose. So basically this PCA can be used to reduce the number of features so that the speed of model can be increased. Thank you.